The load factors in the various combinations cover 95% of the situations engineers will see, but we need to be able to handle the special cases as well. If the unfactored internal force or reaction for all load types has the same sign, we can use the load combinations just as they show up in the standards. The difficulty is when different loads cause opposing effects, some positive, some negative. For example, consider the weight of the cables attached to this tower. Let's look at the effect of each cable location on the vertical reaction at the lower left corner. We can label the cables A, B, and C. If we consider the load at A, it causes counterclockwise moment about the bottom right corner, so to balance that out, the vertical reaction needs to be up. If we consider the load at B, it also causes counterclockwise moment about the bottom right corner, so it also causes an upward vertical reaction. The moment arm is much smaller, so the upward reaction is smaller. But look what happens from the load at C. This load causes a clockwise moment about the bottom right corner. That means we get a downward reaction on the left side to keep the tower in equilibrium. If we ignore load factors, the net effect of the three cables is this upward force. The cables will probably always be there, and their weights are known pretty well, so we would likely consider them dead load. If we use the load combinations from the ASCE standard, the load factor on dead load effects is typically 1.2. That increase accounts for the possibility that the cable weighs more than expected. That could occur if the cable has a bit more sag than planned, so it would be longer, or if the coating on the cable is thicker than anticipated. When I'm designing the left support for vertical force, I want to consider that the dead load causing upward reaction might be bigger than anticipated, so I use the load factor of 1.2 on the effects of cables A and B. But what about cable C? That cable helps reduce the vertical reaction on the left side, so this would be the net force. But if I amplify the dead load effect of cable C, it reduces the net vertical reaction even more. Should I count on cable C having extra weight when I'm trying to find the design vertical reaction for the left? Remember, the design value is the one we need to design for. Counting on extra dead load in cable C to reduce the design value seems like a bad idea. So when different loads cause opposite effects for an internal force or reaction, we don't want to amplify both of the opposing effects. That would be dangerous. Instead, we want to consider the possibility that one of the opposing effects is the smallest it can reasonably be. With rare exception, the load factors in the combinations provided in the standards are the largest values we need to consider. But as we saw in the cable tower example, we want to use the smallest reasonable load factor for opposing effects. For load types like live, snow, and wind, it is reasonable that the load might not occur at all during the critical time when other load effects are maximized. There are days when there's no snow on a structure. There are days when there's no wind blowing. The smallest reasonable load factor for loads that might not be occurring is 0. Think about how that applies to our cable tower example. If cable C might be removed for maintenance, we should consider the lower bound factor of 0 for that load effect. If the load factor on the effect of cable C is 0, we get the largest vertical force at the left support. What about loads that will reasonably always be there? Using a load factor of 0 is unnecessarily over-conservative, but it is possible that they are a bit lighter than we expected. Fortunately, the committees creating the standards have already determined a reasonable lower bound load factor for loads that will always be present. From the ASCE standard, that factor is 0.9. That is the same as saying we are going to consider that the load effect is 10% smaller than we expected because the effect is helping. For our cable tower example, if cable C will always be there, we should decrease the effect of its weight by the factor 0.9, and we get this design vertical reaction. So, to reiterate, the load combinations in the standards already adequately cover the largest values that we might need for load factors. But it is our responsibility to consider using lower bound load factors when there are opposing effects.